Hello everyone, welcome back on the course of HAT surveying, and we are in module 6 photogrammetry. In the last lecture we discussed about the vertical photogrammetry, wherein we said that we are acquiring one vertical photograph and then we realized that because of some error which is unintentional in nature, it could be a little tilted also. And then we defined two terms, which is vertical photograph, that is an ideal situation, and another one which is a real practical situation we call the tilted photograph. In case of vertical photograph, we assume that the optical axis of camera and the plumb line passing through camera are coinciding or they are matching exactly. And as a result, we have derived some of the formulations for ideal case. Then we have also seen that what could be the possibility in case of the tilted photograph. Moreover, we have also learned what is the relief distortion or relief displacement, and again we have learned what is the tilt distortion. Also, we talked about the scale of vertical photograph and tilted photograph. And what is the scale? In case of map, we define scale as a ratio of the distance measured on the map to the distance measured on the field between the 2 points. Similarly, in case of photo scale, we have defined scale of the photo equal to the distance measured on the photo to the distance measured on the field. So these are very simple terms. Now you are able to understand very easily. Today we are going to talk about stereo photogrammetry. Let us go into the lecture today. This is the lecture 3 on the module photogrammetry, and this lecture is about stereo photogrammetry. Okay. So these are the books. Still I will say these first 3 books are still appropriate for this lecture. Right. Now let us understand what is the stereo vision. Okay, right now let us say I am looking at a point, these are my 2 eyes, and right, I am looking at a point here which is a point called A, and so my eyes are having this kind of rays intersecting at the, and this angle is formed. Now what if there is another point B and I am looking at this point B here, and so if there is a difference between H and B that is very evident from this slide. Let us say I call this angle as alpha and I call this angle as alpha dash. Here you can see that alpha is more than alpha dash. Why? Because the point B, it is far away from me compared to point A, and that is the what we call as stereo vision. That means I am having 2 eyes, they are intersecting at a point, let us say right now camera, or I can say the point is camera and there could be another point which is behind the camera. So this point A is my camera and B is the point which is behind the camera. So I can easily say that I am percepting the depth, or I am measuring the depth, or I am trying to understand or perceive the depth because of the stereo vision. Okay, what is the contrary argument to that? Okay, let us do one experiment, and you might have done it many times before also. It is not a first time you are going to do, but let us repeat this thing. So let us say there is a point A in your room, and try to stretch your arm like this and make your finger this way and try to hide the point with your finger. Fine. After doing this thing, what will you do now? You will close your one eye, let's like this, and try to see from the one eye, that hided point. So pointed hided behind the finger, and you are closing your eyes like this. Okay. So once it is done, you open this eye and close this eye. You will find out that the point which is hidden behind the finger is shifted, and this shift is called the parallax. Well, we use this term also in astronomy to find out the parallax angle, and the term parallax is coming from the similar concept. That means on the successive exposure of the eye, there is a shift of the point, and this shift is called parallax. Well, so now if I have, let us say, my left vision here and this is my right vision here, right eye and left eye. So from left eye, if I close my left eye and try to see point A, right, which is behind my one finger, and then I close the eye, left eye, and open my right eye, you will find out that there is an apparent shift of point A. So that's the idea here, and this is an essential to create the depth perception. Even I have two eyes, but my eyes are incapable of doing the parallax creation. That means I will not be able to see the depth of a point, or I cannot compare two points which are different in depth. So that is called the depth perception using stereo vision, and we are going to replicate the same phenomena in our photogrammetry, and that is why we call it stereo photogrammetry. Well, let us go ahead. Here, before we start, we have to understand one thing, that let us say there is a flight, and flight is mounted, or the airplane is mounted with a camera. So instead of creating two camera, that means for stereo vision I need to have two eyes or maybe two cameras. So what will I do now? I will put one camera, only one camera on a flight, and then the airplane will move in certain direction. So this camera will keep on acquiring the photographs, and as a result I am trying to replicate the eyes or the multiple cameras this way in a line, right? So what is the understanding here? The understanding here is I need to first acquire the data. That is, I need to acquire the many photographs so that I can create some kind of stereo vision. Moreover, if you see, in case of the example which I gave you by finger, there is a point A or point B, but we have assumed that both points A or B or any point, it's visible from the each eye. That means there is some kind of overlap, or there is some kind of common area between the two eye. That is why I can see one point, common point. It could be point A, or it could be point B, or it could be any point. But there is an area where both eyes can see, or both eyes are looking at the same point or the same area. That is why I need to create the same replica or the same thing here with the aerial photogrammetry. So what I am doing, I am trying to acquire the vertical photographs which are like this, and each and every photograph have some overlap with the adjacent photographs, so that I have a common area where my both camera locations are looking at that point, right? So let us see by animation what does it mean. Let us say this is my terrain, and this is an aircraft mounted with camera. So this is the field of view, and it is acquiring photo. Now it has moved to this location, then this photograph, then this, then this, then this, and so on. So I have some, this is my flight direction here. So this is the flying height, I can write here, this is the flying height here, and if I take the average elevation, I can say what is my value of h, or even I can take, so this is my overlap, you see on the ground, this is my overlap which is marked in the photo, is image or slide also. Okay. So this kind of overlap which is in the direction of flight, it is called end lap here. Okay, what if I see the flight coming towards me or going away from me, like this? Let us say same terrain, now aircraft is coming towards me. So again this is my flight direction, that means, so it is acquiring photograph which is perpendicular to the flight direction, this next position, this next position, and so on. So there is also an overlap, and I call this overlap as the side lap. And end lap and side lap both are important and required. Okay, perhaps you might have understood what is the concept of end lap and side lap, that is the overlap in two directions. Okay, let us look into another animation which will explain it again in a little better way. Let us say this is my flight direction and this is the area we want to, okay. So this is the two images in the direction of flight. So this is my end lap, right, and so I am acquiring the photographs like this, right. Further, this is my side lap here, you see, this is my side lap here. Okay, so flight has traveled like this, gone this way, coming this way, like this. Now it is going this way, this way, this way, this way. Okay, then it has come this all along this way, now going this way. Okay, again this is my side lap, and again flight has come this way and it will go this way. And it is acquired the complete photograph for complete area. So these many photographs have been acquired by the arrangement of one camera into a airplane. So this is the way, and each photograph is a vertical photograph. So now I understand that this is called airborne data acquisition for aerial photography. Okay, each photograph is vertical because I want to analyze a theoretical case for depth perception. So the idea here is, how can I find out the depth, or how can I make the map, that is 3D map, using photogrammetry. So let us look into that now. But before that, we should understand that how many photos are required for a given area. And before we go to the field, we have this area in our beforehand, that this is the area I want to do a 3D mapping, and hence I want to acquire photographs for this area. Right. So in order to acquire the photograph, I need to do a preliminary exercise, what we call as flight planning. That means I plan my complete mission of data acquisition, and then so that with the minimum cost I can acquire the data. Okay, so let us see, there are two possibilities here, and I want to find out what are the number of photos I need beforehand, before going to the field. So let us assume that this is the area which is in rectangular in shape, is given to me. Let us see, the area, total area is given by AT, and I call it total area of interest, or I call it AOI, area of interest, the term I am writing here also. Okay, so let us look into that, you know what is the scale. We defined the scale in the vertical photograph, it was f by h. So let us define something called s dash, which is inverse of the scale. And now you see there is an end lap. Let us see, there is a first photograph is like this, second photograph is like this with some overlap, and we call it end lap here, right. So this is my end lap, and I write this end lap as eta e. End lap is nothing but eta is the ratio of the photo length, right, and here the overlap, length of photo. That means I am taking this ratio of this here to here 1 to the total, this one, length of the photo, right. So this is my denominator here, and this is my numerator here, fine, and I call it eta e. Similarly, if I find out the overlap here between these two photographs, this overlap, what we call as side lap, and I write as eta s. Similarly, I will take the ratio of this overlap here and overlap to the this length. Total length is this, width what we call here, fine, and that is what we say, that ratio of this to the ratio of this is my side lap. Now I can say that what is the length covered by each photograph on the ground, and there simple idea is there, because I can say, let us see, this is the length of photograph. So that is an effective, I will say, let us say L dash is my length of photograph, that is travel, or that is effective coverage. Why? Because this is overlap So, in two photographs, this area which is eta e into L, L is the dimension length of the, this is my, let us say Ln length here, okay, and that is called, let us see the small w, width of the photograph. So, L into E is my overlap here. So, if I remove L minus eta e L, then I will get the effective coverage or the real coverage or the real area acquired by the image. Now, if I multiply this by the scale or the inverse of the scale S dash, I will get the total length on the ground, right. Okay. So, this is the total length covered by one photograph effectively, not in reality. In reality, it is covering the complete length with overlap, but because of overlap, I need to say that a photograph on the ground, we have moved by not the L distance, rather we have moved by L minus overlap. So, this is nothing but L minus overlap, and I am multiplying with the S dash, which says that what is the length really covered on the ground, because these dimensions are for photo. So, I am multiplying the dimension of photo with the scale inverse, I am getting the distance on the ground. So, this is the idea. Similarly, I can say that this is the width of one photograph on the ground surface. So, what I do, I will 1 minus eta s, eta is my side lap, and then again S dash multiplication, and this is my width of the photograph. So, I marked here what is width and what is length L. Okay. So, what is the area covered by effectively the covered by one photograph? So, that is nothing but A L into W, right. Now, I can write this thing here, and this is nothing but this. You can do it yourself also, this mathematics, it is very simple. Okay. Now, if this is the total area of the AOI, and if I divide by the area covered by one photograph or area effectively covered by one photograph, so I will come to know what is the number of photographs I need in order to cover the whole area AT. So, this is what we call the number of photographs required in order to develop the stereo vision for the whole area AT, area of interest. Moreover, I would like to say few of the things about the overlap. The first of all, the overlap eta e, that is end lap, that is minimum 50%, and in general it is kept 60% as minimum, because if I have 50% overlap, what will happen? You can see, that means if I have this photograph here, and if I exactly have the 50% overlap, it will be like this, and in order to avoid any chance that I can, because of some random error I lose it, what we do, we minimum keep 60% end lap. That means I am having this much of overlap like this, fine. Similarly, what about the side lap? Side lap is kept in the range 25 to 40%, and that gives me the continuity on the between the different lines of the flight lines or different lines of data acquisition, the side lap. So, that is the idea here. Moreover, I would like to say here, this is the swath, and this is the swath along the flight line. Right. So, I am saying that this is not small l. So, here I am showing swath as on ground as L, and swath along the flight line is nothing but W, and they are called the effective swath basically. Both are effective swath because they are removing the overlap area, right. So, I can say here that what is my swath? So, it is my effective swath here, L and this one. So, I should write here swath is nothing but W into S dash, and here what is the swath along the line? Length multiplied by S dash. So, what is my capital L on ground? I call it effective swath along flight line. And similarly, W is nothing but effective swath. Right? Okay, so let us move ahead. Okay, number of photographs when situation is again slightly different here. Let us say length is given to me instead of area. So then this is the way we again will cover the photographs. Yes, so we have covered all the photographs. So let us go to the next slide where I write this is the effective length covered on the ground. Similarly, I can write effective width by covered by one photograph on the ground. Okay, so what about the number of photographs along the x direction, along the flight direction? Okay, here if I divide this Lx by L, you can argue like this: if you divide Lx by L, so then in that case I should get number of photographs. But there is a slight issue here. I need to cover the whole terrain, or I need to derive my 3D stereo view for the whole area of interest, and as a result what happens, I need one additional photograph so that the last photograph, which will not be able to cover the area, or which will just cover the area in one photograph, I want to cover that area in two photographs, and as a result beyond the boundary of the area I need to have one more photograph, that is the last photograph, that will have end lap. Similarly, in case of side lap, I need to have some additional photographs on the another edge on this side, and that's the reason we write it. The total number of photographs are Lx by L plus 1, which is given here. Similarly, I have Ny as Ly divided by W plus 1. I need one additional photographs. Now, total number of photographs I can say Nx into Ny. Again, I will multiply here this thing. So, okay, what next? So, you can see now I can also calculate the interval between the consecutive exposure. That means this is one photograph. After some time aircraft moved to this, it created another photograph, and so on. So, between the two consecutive photographs, what is the time I need? So, what is the time exactly there in the field? That is nothing but if I divide this distance L by speed of the aircraft. So, we will get that is then interval between the consecutive exposures. Let us go ahead. Okay, there are two phenomena while we acquire the photographs. One is crab and another is drift. So, let us look what is the crab first. Let us see, there is a photograph like this and flight line, they are acquired like this. So, this is my flight line in this direction or the flight direction, and the photographs are not aligned with the flight direction. Ideally, it should be like this, the way we have said in the previous slides, but it is happening that way. So, this line if I draw and this line is in flight direction, this angle is called the crab, or this effect is called the crab effect. Similarly, what is a drift? So, drift is this. Let us say I am acquiring photographs like this and there is a wind, and because of the wind what will happen, I am flying, the flight is in this direction, but because of the wind every moment, so once I fly this one, there is a wind, flight will go like this, again it will go like this, it will go like this. That means it is effectively going this way, and because of that even the photographs are aligned with the flight direction, but they are having some shift in this direction. So, these are the shifts. You can see here the photographs are shifted in up direction, and that is called a drift of the wind sometime, or wind drift. So, because of the wind we have drift, and because of the misalignment of the flight direction and the aerial photograph axis I have. So, that is the idea, and these are the basically limitations in the aerial data acquisition. Fine. Now, I want to do the flight planning, and for that I need to have some kind of computations. So, there I need to have some kind of idea because we want to calculate the scale. So, I need to have focal length, I need to have h, okay, size of the area of the photograph, or that is nothing but we call it area total, or it could be like Lx and Ly, whatever. So, I can write here or. I need the dimension of the area of interest. Size of the photograph, that means I need length as well as width of photograph. Longitudinal overlap, that is my end lap. I also call longitudinal overlap. Lateral overlap, the side lap. Okay, and position of the outer flight lines with respect to boundary of the area. Fine. So, what is a flight track basically? Okay, scale of the flight map, anyhow I will calculate it, f by h equal to s, or s dash as my h by f. That is basically the scale of the flight map, the desired one, and according to desired one, if I have the camera of focal length f, I will decide my h first, that is flying height, what should be flying height, and then I know that there is a limit of the capital H, and hence I have a limit on the scale of the flight map. Then we have ground speed of the aircraft, that is speed v. So, if I have this all information, I can plan my work beforehand, before going to the field, and that is what we call flight planning. This is the flight planning computations. That means I want to acquire the data in the field. Before that, I do some exercise where I know which camera I am going to use. The moment I fix the camera, I know what should be my flight height or the flying height for the given scale, or to scale to be achieved in mapping or aerial photographic mapping. So, I know this is whatever scale. For example, if I have 1:10,000 scale, which is very high, right. So, for accordingly I will decide what should be the flying height h, because this flying height a pilot needs to fly the aircraft at. So, once it flies at flying height h, the photographs will be of the scale f by h, because f is the focal length of camera. Now, I already know this information. The moment I fix the camera, what is the length of the one photograph and what is the width of one photograph. Thirdly, I know what is the size of the area of interest. Okay. Then I fix my end lap as minimum 60%, or I can write it as more than 60%. Similarly, it will be in the range of 25 to 40%, the side lap. So, the moment I fix it, I can find out the number of photographs n, which is nx and y. So, what could be the possible cost in the field if I acquire so many photographs? So, beforehand I know what will be the projected cost or what is the likely cost. So, should I go for this kind of mission? Because what is the accuracy I am going to get by this data acquisition in my real map? Does it really worth to go for this exercise or the data acquisition or to create such map by aerial photography? So, that kind of judicious decision I take by flight planning only, and that is the importance of flight planning, right. And so, let us see that we have acquired the photographs. That means I want to now decided that yes, by flight planning I have decided that yes, this mission is worth. That means I am going to create the 3D view of the terrain, and that is going to have enough impact, in a sense like this cost is justified. And so, let us go for the data acquisition. So, once I acquire the data, that series of vertical photographs having some end lap and side lap. So, now I want to create the 3D using parallax. Okay. So, let us learn what is the parallax again in terms of aerial photogrammetry. So, let us see there are 2 points A and B on terrain, and then we have this point as my exposure station, then another exposure station O dash, first image, second image. So, that is my principal point K, and similarly I have focal length here, and there is another principal point K dash for next image, and then we have focal length, because camera is same in 2 consecutive photograph or in the whole mission. So, I am writing the same focal length f. So, basically this is one camera only. Now, the point A is acquired like this. Similarly, point A is again acquired in the another photograph. next photograph. So, call A dash location. Fine. Similarly, let us go for the point B, B and like this. So, the image of point B in two photographs are B, B, B dash. So, let me call this as my left photograph and that is my right photograph, and we are going from here to here by flight. So, these are my images like this. This is my center line. So, point K here, point K there, now K dash and K dash here. You can imagine that both points are appearing in each image because we have 60% overlap. In case we have 50% overlap, K dash would have come at this point here, but now we have 60% overlap, that is why point K dash is appearing inside the image or photo, first photo. Similarly, point K is appearing here and not there. Okay, so this is the fine. You can see this point A was here. So, this is my XA, that is the x coordinate of point A in first image. Similarly, I have point B here, so I have XB here, you see in the animation. So, try to look carefully in the animation. I am going very slow here. Again point A dash, so I have B dash, so I have XA dash and XB dash. You can see here that XA and XB are positive in left image, but XA dash and XB dash are negative because they are on the left hand side of the this. So, this is my coordinate axis here. Let us see x dash, y dash, and this is my coordinate axis here is x and y. So, I am measuring XA and XB as positive in left photograph, but in case of second photograph I am measuring them as negative from this origin, right. Now, let us replicate these points A and B on the left image. From here I am trying to replicate these 2 points on the left image. So, this is the point B dash and A dash like this, and so here B dash and A dash. You see, I just place them here. So, nothing but with respect to this origin I place these things here, and now I can write this is my XB dash, this distance which is equal to this distance. Similarly, this distance is my XA dash. I hope you understand the simple idea. Okay. So, can I say that this distance between point A and A dash, basically it is the shift in the location of point A on successive exposure. Remember, we have done the experiment, we close our first eye, then we close second eye. So, there is a shift in the point. So, this shift is equivalent to this XA and XA dash, because at first exposure it was captured here or here. After some times there was second exposure, so it was captured here. So, there is a shift here, and since it is in the negative direction, I am putting it into this negative direction here. So, that is a total shift. So, I can write here XA plus XA dash, rather I can say numerically it is equal to the parallax of point A. I can write also here like XA minus XA dash, because it is a negative coordinate. So, I am basically taking the algebraic sum of the two locations with respect to their corresponding image centers. Like similarly, I can write here PB is nothing but XB plus XB dash, which is nothing but XB minus of XB dash here, since it is again the negative coordinate, and so in fact it should be XB minus XB dash, but it is itself is negative, and I get XB plus XB dash as my total parallax. So, that is the shift in the location of point on image because of the two successive exposure of camera. I hope you got the idea of parallax on the photograph now. Earlier we have done with our eyes, understood the concept with eyes. Now we have done with this camera, and now we understood that on the photograph what will be the parallax or what is the shift in the point because of the two successive exposures. Let us go ahead. So, here it is my PA and here it is my PB marked here, what I written here. Okay. So, in order to find out the 3D coordinates, I need to find out x, y and z coordinates. So, So let us first find out the x and y coordinates. The moment I find out x and y coordinates, then I will find out z coordinate, and then I can say that since aerial photography is acquiring all the things together, I am developing a simultaneously measurement of x, y and z system, but mathematically I am doing separately. So let us look into this thing. So that is one triangle here, and if I draw the similar triangle, so then I can write this thing OK divided by OK, capital OK, equal to this ratio and equal to this ratio. You can do it yourself again, fine. Again, OM is nothing but focal length, and that is OM capital is nothing but h minus h. So thirdly, if you look at in the similar triangle, KM is nothing but small x, that is coordinate of point, any point, and here it is the coordinate of same point in the on the ground. So now I can write it very easily. This is one way of expressing it. Similarly, if I write for y in the same photograph, you see there is an animation. This triangle and this triangle, yellow triangle and red triangle, are similar triangles. Using this, I can also write like this, or like this, or like this. Well, again this OM by here same, and here you are calculating this one, which is nothing but y by y. So I can write this is my, given the y coordinate in the image, I can find out the capital Y coordinate on ground, provided I know the focal length as well as flying height and the height of the point, right. So that is nothing but a scale at point, okay. You see in this second photograph, again this is triangle, this is similar triangle, and so I can write this thing, okay. I am using the same term here and I am writing this thing. So for this second photograph, so it is x dash. Similarly, I can write with this triangle shown here, you see this, after this triangle and this triangle, they are similar triangles, so I can write the y dash also, fine. So that is the idea here, that using y dash I am writing the y, knowing the scale of the photograph. Also this is equal to this, okay. So we have find out the ground coordinates in some way, so that is my this one, that is also true as we proved in the last slide. So y equal to y dash like this, and it is my parallax here. You see in the just look for the animation again. So I am writing here P, this term, so f upon h is equal to P by B. Similarly, I can write that B into f, I am multiplying here by B, okay. What is this process? If you just look at carefully, this process we start with the height calculation. Here we have done the planimetric coordinate calculation, that is x and y calculation, right. From here we start the height calculation, so we are writing this way. So I got that this expression, that means this is my x and y planimetric coordinates, and here I can say this is my height information h, and I can also write it this way. Yes, using this information now I am writing this. You can see here this I am replicating here, so B by P here, fine. Similarly, I can write y equal to B upon P into y. So it is basically I am doing all the calculations together. Here you can see here very carefully, I can find out h as h minus Bf upon P, and P is nothing but a parallax of any point. So I am deriving a generic expression. So this is the height of the point. So once I know the height of the point, knowingly that this is my parallax, this is focal length, and this is B. B is nothing but, it is called the air base. The distance between two successive exposure of camera. It is called air base, or sometimes it is called the base also, or distance, base distance also. In some of the books you will find out the distance of base, base distance, base, air base, like that. So, now you can see that I have done the calculations simultaneously for height as well as x and y coordinate, and here this is my x and y coordinate, and here it is my third dimension z, the h height of a point. You just relook into the animations again if you have any doubt, but remember these are the very straight calculations. Fine. So, I am writing here is scale of the photograph, and I am deriving what is the P, B and everything. Okay. So, let us start again. Now, I want to find out the elevation difference of 2 points. So, I have already shown you how to calculate elevation of a point. Now, I want to find out the elevation difference, and there is an advantage that we will see now. So, let us see there is a datum and there is a ground and there is a point A which is height HA above datum. Now, point B is there which is exactly above the A, and this has height HB. So, O point is there and it is a exposure station, and so this is my image. There is another exposure station O dash, and this is another image which is we call consecutively captured images, right. This is the vertical line, principal point K, principal point K dash. Now, this is my flying height H. So, there is a point K, okay. So, try to acquire point B. So, I have image of point B like that in the left photograph, call it a left and call it a right. Then I have image of point A is A. Fine. Then I have A dash and B dash in the right photograph like this. This is my base. So, this is my point B A dash, and this is the point B dash on the image. By animation, it is the purpose is to make you clear how that imaging has happened, or how images are acquired, but it happens in one single flash or single attempt like this. It exposes, the camera exposes and the light comes and it acquired so fast in microseconds, milliseconds. But here the purpose of animation is to show that how things are developing or how we are thinking about the whole process, right. Okay. So, now can we write the equation of parallax? You can see here we are now talking about the relief displacement in some sense. You can see that point A or point B, because of the height difference, let us say that it is a building and building height is represented by A and B. So, I can see what is the change of the location A. A has come to B because of the relief displacement of the point at A, because it has a height HB minus HA. These concepts are there, they are very, very intermixed concepts, very nice concepts we have derived about the relief displacement in last lecture. So, now we are using the basically relief displacement in order to find out the third dimension or the Z dimension, but using two photographs, not the one photograph. That is the idea here. So, try to see. So, that is the XA coordinate. Similarly, I have XA dash coordinate, right. And you remember that we have calculated the parallax. So, this is my XB and this is my XB dash. Well, I hope you agree with XB dash and XA dash. So, now I can calculate what is my PA, it is this one. So, I am writing it in the mathematical terms, not in the numerical terms. So, it is like this. So, the moment I write algebraically, in this particular case, it will become XA plus XA dash, because XA dash is negative. If I take this direction as positive x, it will become negative. So, if this is the positive x here, right, positive x here, so it should be negative here, right. Okay. So, I can write this parallax like this, fine. So, this is the kind of mathematical term here. Similarly, I can write PB like this, and again the difference of the parallax. Now, I am calculating delta P, which is difference of parallax A and parallax B given by this. Okay. So, now I also know from the previous slide, this is the reality, or this is the formulation we have done before. Okay. So, now I am writing the same expression for point A, that means I am putting PA here, and that is it. Similarly, HB I can write like this. So, if I am measuring the parallax of point B, I can write HB. If I am measuring the parallax of point A, I can write HA. Okay. But I want to find out the height difference of A and B, that is the height of the building, because it is a vertical height of a building, right. So, let us look into that now. So, let us do some derivation by hand. So, HA is nothing but HA minus H capital H minus B into F divided by PA. Similarly, I wrote HB is equal to H minus B into F by PB. Now, I can say delta H, which is difference of 2 points HB, because HB is higher and HA is smaller than HB. So, I can write here H minus BF upon PB minus H upon BF upon PA. I hope you agree with that. Further, if I calculate this term, it will be H will cancel with H because of the minus sign, and I will have BF upon PA minus BF upon PB, or BF into 1 minus PA minus 1 upon PB. I hope you agree with this term at least. So, you can do it yourself, try to practice with me. So, at least you will also have a command on the derivation. Fine. Now, what next? I can write delta H, this term as, if I do the simple mathematics again, BF into PB minus PA divided by PB into PA, like this. I hope you are doing with me. Try to do yourself also, right. Okay. Let us call this term as delta P, or the parallax difference, not the height difference. So, delta P is my parallax difference, PB into PA. So, I can write here where delta P is nothing but PB minus PA, right. Okay. So, I got a formula where I write delta H in terms of parallax difference and parallax values. I am writing it again as delta P. So, you see that how the delta H is a function of delta P, that is the height difference is function of parallax difference, or I can see if I multiply the parallax difference by this term here, I can get the height difference, where B is my air base, again I repeat, or the base height or base distance, or the base, also called base, right. PA is the parallax of point A, PB is my parallax of point B. Then we have delta P, parallax difference of A and B. Which is nothing but PB minus PA. So, let us look into this thing. That is one expression, I got it for my height calculation. So, I am measuring delta P from the image, and now I am calculating the delta H. Okay, so let us write PB equal to PA plus delta P from here. I am writing it this term. So, I can replace the PB because I want to have minimum number of variables. So, I can write here delta H, that means I am replacing PB with PA plus delta P into delta P, right. So, that is the expression where I have minimizing number of variables. PA is there, PB was there, I removed the PB in terms of PA. So, I have delta P because I measured from the image, 2 images I took and I measured it by some way, and then I have PA which I already measured from the image. So, like this. Okay, so I can write this thing here that this is the expression I have. Fine. So, let us look into the another form of this, and what is written in the books called alternative form. If you are reading the book suggested here, okay. So, let us look into the so called alternative form. It is nothing but alternative. In the books it is written alternative form, but no problem, there is another expression I can say. Again write HA equals to H minus B F upon PA and HB equals to H minus BF upon PB. Right. Now, I want to do the same exercise, but in terms of not in terms of delta H, in terms of delta P. That means, I want to calculate what is the change in the parallax if there is a change in the height. So, let us do like that. So, calculate PA from here. I can write here, see that how to write it, BF upon, can I write this way, H minus HA. Similarly, I can write PB, B into F divided by H minus HB, right. So, let us calculate the delta P. It is nothing but PB minus PA, which is I can say here B into F upon H minus HB minus H minus HA. Okay. So, let us divide this slide, and here from here again I am writing here that delta P is equal to BF into 1 upon H minus HB minus 1 upon H minus HA, or delta P is equal to, I am doing simple mathematics, nothing special, H minus HA minus H minus HB divided by H minus HB into H minus HA, again equal to B into F into H will cancel out here, and then we have HB minus HA, then we have here in denominator H minus HB into H minus HA. I can write there delta P is equal to, if you remember, B into F into nothing but delta H. Like this, where my delta H is difference of height that we already defined before also, right. Now, I calculated the parallax difference or the difference in parallax. Now, it is better to write again the HB and HA here. So, we can write here HB as HA plus delta H, and again we will put it here so that I can minimize my number of variables. I write here now delta P is equals to B into F into delta H, which is here H minus HA into H minus HB, I write HA minus delta H here, fine. Okay. So, there I can calculate delta P is equal to B into F into delta H into, I am now multiplying it inside H into HA, that is I am writing it like this, H minus HA inside term minus delta H like this, and I can write it like this, B into F into delta H divided by H minus H A whole square minus delta H into H minus H A, right. Okay, now do some kind of transformation shifting. So, I can write delta P into H minus H A whole square. So, that means I am multiplying it up here minus delta P into delta H into H minus H A equal to B into F into delta H, right. So, you have this term now. So, there I can easily write now that I want to calculate delta H basically in terms of delta P with this formula. So, let us shift this term on this side. So, once you shift it, you will get H A. Okay, I take this term common, and then I can write here delta H into B F plus delta P into H minus H A equals to delta P into H minus H A whole square. So, we expressed the height difference between the 2 points delta H as delta P H minus H A square divided by delta P, which is difference of the parallax of the two images for the 2 points like this. Okay, so can we replace the airbase B with the help of flying height or in terms of flying height, so that we can reduce one variable in this equation. So, let us see what is the relationship between flying height H, airbase B and focal length F. Okay. So, let us imagine that there is a airbase B and there are two exposure stations or perspective center of two images, all right. So, from these two places a point in both images are acquired. A point is acquired in two images. This is the left image here and that is the right image here. So, this is my focal length from here to here, okay, and this is the flying height H here. Okay. Now, you can see very easily here that let us say that this is the principal point K of first image and this is the principal point K1 of the right image. Now, since the two images have overlap, a common overlap of 60% or so, what will happen if I draw these two images left and right? So, the left image will have point K1 around center and similarly it will have point K1 along the flight direction. Now, this point will have, this image will have point K here and at the center it will having K1. So, if we align the flight direction, which is this and this here, what will happen? The distance between the 2 points here in this one image is my image base B. Okay. So, this image base B is just an representation of my airbase B. Why? Because that the real terrain or the 3D condition or the 3D topography of the terrain is, image in an image, it has been photographed in an image with the help of focal length. So, my focal length is basically representing the flying height H. All right. So, from here you can develop some kind of triangles and then using this triangle logic I can say that the airbase B and the image base B are basically connected but how are they connected? Now, if you take the ratio of B air base to flying height, I can see the same ratio exists between the focal length and the image base, alright, because this point K1, let us say, is here, right. So, this is my image base B from here to here, and now I can write it very easily using the similar triangles, that B upon F is equal to capital B by H, because they are in the same ratio. Why? Because the image geometry, which is using the focal length F, it is recreating the same scenario at some small scale, and that is why we can write this ratio easily here, and you can also prove it by the similar triangles. And as a result, now I can write that B into F is equal to H into B here, and now I can replace this term here in this thing, and I can reduce one variable. So, what is the final result here? That delta H is equal to delta P into H minus HA square divided by delta P into H minus HA plus H into B here. Fine. So, how to find out this image base B? We call this image base term B here, and how to find out? Well, we can take in practical, how do we do it? We take the 2 points, or first we try to find out the location of the principal point K1, which is the principal point of the another image. So, we find out the 2 locations K and K1 in one image, and then we measure the B for the left image. Similarly, we also measure the B for the right image, and then we take the average of the, let us say, B2 and B1, and then we define B equal to B1 plus B2 divided by 2. So, in the real practical case, we find out B like this, and we call it the image base here. Here I am writing here this way, delta H equals to, finally what we got here, delta P H minus HA square divided by, I have here delta P into H minus HA, we have derived it today, this term, into BH. Now, what if I take point A, take point A at datum, right. So, it will give me the height of point B with respect to datum or point A, because point A is on datum. So, I will get the height of point B with respect to datum. As a result, HA becomes 0 here, because we are putting on datum and we are measuring every height from datum, where the height of datum itself is 0. So, now I can write here delta H equals to, let us say, delta P into H minus HA 0 whole square divided by delta P H minus again 0 plus B into H, or it is nothing but delta P H square into delta P H plus B H, or I can write delta H equals to delta P. Now, you can find out very simple term, we are cancelling H with H, and so I get this term. So, this is nothing but HB minus HA. So, HA is 0. So, this is the height of point B above datum. So, I can write any term like that, the height of any height point, let us see, I call it any point H, equals to delta P into H divided by delta P plus B. I hope you agree with this term. So, what we are getting here, right. So, this is a basic very simple formula finally we have devised. So, it is nothing but the height of a point above datum, right. Okay. So what is the interpretation here? Interpretation is very simple. And interpretation is that if you assume any point at datum, that means datum is passing through point A, and point A itself is on the surface of earth, that is the building, bottom of the building. You assume that the datum is passing through the bottom of the building, and as a result you can find out what is the height of the point with respect to the bottom of building. So even you can calculate the height of a tree with respect to that bottom of building, and what is the height of a top point of the building, because you are putting your datum at point A, which is at the bottom of the building. So that's the idea here, and that's the interpretation of this formula. Now what about the accuracy of your height measurement? So let us look into this thing. So it was like this kind of term we have derived, Bf upon P, or I can write H is equal to H minus Bf upon P. From here I can write the dH equals to, I am differentiating it, 0 minus B into F upon P square, and I can say here minus into dP, right. So I will get dP into Bf upon P square. So that is the error in the parallax that will give me this kind of error in height measurement. That is the idea. Okay. Similarly, I can write here, if you remember the law of error propagation, you use it on this formula. Assume B and F are constants, then you can prove that sigma H is nothing but equal to sigma P and Bf upon P square will come. Try it yourself, I leave it to you. So one more expression is there of the height measurement, okay, that is nothing but, now write P is equal to Bf upon H minus H. From the formula we know that H minus H is nothing but equal to Bf upon P. So I am writing from here this formula. So there I can also say what is my dP. If I differentiate it, B constant, F constant, but H is not constant. So I write H minus H whole square minus and minus dH, right. There I will get it, dP is equal to, again minus and minus will go, and then I have dH into B upon F into H minus H whole square. So I can write here also that sigma P is nothing but sigma H into Bf upon H minus H square, and there I can write it sigma H or dH is equal to H minus H whole square upon Bf into dP, or I can write sigma P also, right. There finally I write sigma H is equal to, or dH is equal to H minus H whole square divided by B into H, which is nothing but Bf into dP. So finally I write as dH is also given by dP into H minus H square divided by B into H here, right. And therefore I write here sigma H is equal to, I can also write like sigma P into H minus H whole square divided by BH, like this, and this two formulas we have. So there I have two expressions, and in the books it is written as unit height or unit change method. In fact, it is nothing but unit change. I am try to find out what if I make a unit change in the parallax. So what will be the change in the height? And that's why they name it unit change method. But in fact, we are just doing a differentiation, or we are using law of error propagation to find out the error in the height measurement given the error in the parallax measurement. Okay, so let us look into the how do we do this thing using some instrument. So this is the instrument what we call as stereoscope. We have two types of stereoscope. One is called mirror stereoscope, that you put two images, and remember that two images are aligned in a way that flight lines, that means if I go back to the slide, last slide, that's a blank slide. So there are two images, one is left image, call it left image, and the right image. Here in the all derivations we have assumed this is my flight line like this is my x and y axis, or this is the flight line from here like this. That means here I assume that I have already aligned the flight lines of the two photographs which are consecutively acquired in the same flight. So by that I say that this, once you align the flight lines of two photographs and you keep it like this, then you can do this operation using stereoscope. So there we do, what do we do here? We put these two photographs such that their flight lines are aligned, correct? And then once you align it, you can see the 3D view using the mirror stereoscope. In the field, mirror stereoscope is difficult to carry, although sometimes people carry it if work is so intense. But in the field, you want to have kind of relief idea of how terrain is varying in 3D. So you use pocket stereoscope, which is of very few grams, 50 grams, even less than that. The mirror stereoscope is little heavy, around 1 kg or so. So you carry the pocket stereoscope in the field, you take two photographs and you try to see how the terrain is varying, and you take some decisions in the field. And that is the instrument used for the stereoscopy. Remember that you have to align two photographs in such a way that their flight lines are along a straight line. And that comes by trial and error, by experience. I hope if you have some instruments in your college or university, you should try it. And for taking the photograph, now you can use any camera like mobile camera and try to develop in your room, put two objects which are slightly away from each other, having some kind of depth difference, and then try to acquire the photograph from two places, one from here, one from here. So this is left and right photograph, and take the print out of those photographs on a simple paper, put on the mirror stereoscope, try to align the flight line which is from here to here, this is my flight line, and try to see whether you can see the depth of the 2 points or not. And you can also find out the relative height of one point, assuming that another point is at 0. Try to do yourself. It's a very interesting exercise. Stereoscopy can also be done with the help of computer and what we call computational photogrammetry, and that computational photogrammetry is also called analytical photogrammetry, and that we have to learn it. So in the coming next two lectures, L4 and L5, we will learn the analytical photogrammetry, that how computer does these same operations, but it will use some kind of mathematics, matrices, because computer does not understand what we say or what we understand. It understands language of mathematics. So in the coming two lectures, we will talk about analytical photogrammetry. So till then, thank you. Bye-bye.